Water flows into a large tank with a flat bottom at the rate of 10 raised to minus 4 meter cube per second. Water is also leaking out of a hole of area 1 centimeter square. So here there is this hole out of which water is leaking out. If the height of the water in the tank remains steady, then what is this height? So this height they have given to remain steady. Alright. So the first order of things over here is to realize that the height is remaining steady because the incoming rate of flow of water. So let us say water is incoming. So the incoming rate of flow of water that is coming in. Okay. This incoming rate of flow of water is given to be 10 raised to minus 4 meter cube per second. So this is nothing but the rate of flow of volume, d volume by dt. Now this incoming rate of flow should match the outgoing rate of flow. Only then the level of the tank will remain constant. Or level of water in the tank will remain constant. So in order to maintain this constancy, no net incoming mass or outgoing mass should be there. And hence incoming water should completely go out. That is when the amount of water in the tank is going to remain constant, and hence the level of this water is going to remain constant. Alright. Now we would just like to find out what is the rate of flow of outgoing water. So this rate we would like to find out. We understand that d volume by dt is nothing but volume can be written as area into dx by dt. So this can be written as area into dx by dt is nothing but velocity. So we know already from continuity equation that d volume by dt is nothing but area into velocity. So for the bottommost point, we already have the area and we would like to find out the velocity. In order to find out the velocity, what we do is we would apply Bernoulli's theorem at any point on the top, and we would apply Bernoulli's theorem at the point wherein the water has just come out of the tank with, let us say, v velocity, the velocity which we would like to find actually. So let us say this point is the topmost point T, let us say, and this point is the bottommost point B. So at point T, let us say at T, if we were to write down the terms in Bernoulli's equation, so this point T is exposed to the atmosphere, so the pressure is going to be atmospheric pressure. Alright. Plus, this guy has zero velocity because the level of the water is constant in the tank, and hence this guy is not really decreasing in height or having any velocity. So half rho 0 square will be the second term, which would be the energy per unit volume term. And the third term, the potential energy term, is going to be there. Let us say we take the bottom of the tank to be the reference potential energy level, then this point is at a height h, essentially speaking. Now since it is at a height h, its potential energy is going to be rho g h. Alright. Now this is at t. This is going to be equal to the Bernoulli equation terms at point B. So at point B, what is happening? B is also exposed to the atmosphere, so pressure at point B is also going to be P naught plus the velocity of point B has to be found out. So the kinetic energy per unit volume term would be half rho V square, and the potential energy term at B would be 0 because it is at 0 height compared to our reference height, which is the bottom of the container. So this is the term at B. Therefore, we can clearly see and understand that P naught is getting cancelled, and this term is 0 and this term is 0. Then from the remainder of the terms, rho is getting cancelled, and we can see the standard result V to be equal to under root 2gh, which is typically the case in many Bernoulli equation systems. Alright, so now that we know the velocity of the bottommost point, we know the rate of flow of volume of the bottommost point essentially. So the rate of flow of volume of the bottommost point would be A into V, that is equal to 1 centimeter square. Okay, so that has to be converted into meter square. So 10 raised to minus 2 square, that is 10 raised to minus 4 essentially, into under root of 2gh. Alright, so this is the rate of outflow of volume from the bottommost point. Now only and only if the rate of inflow matches the rate of outflow, then in that case the height is going to remain constant or stationary. This we have already understood. Writing down the equations equating the rate at which water is incoming, which is given to be 10 raised to minus 4, with the rate of outflow, which is given to be 10 raised to minus 4 into under root of 2gh. From this we get 1 is equal to 2gh. That implies h is equal to 1 upon 20 meters. So 1 upon 20 meters is going to be 100 upon 20 centimeters. I am taking the value of g to be 10 as of now. Let us see. So this is going to be, I am writing the approximate sign over here because the exact value of g is 9.8. So this is going to be approximately 5 centimeters. So we are looking for an answer around 5. We have an answer 5.1. So why is the answer 5.1 and not 5? Because they must have taken the value of g to be 9.8 because it is not specified. So that's okay. We'll get an answer that is slightly more than 5, which is okay. The answer is going to be 5.1 over here in this question. So again, recapitulating, I have basically used the Bernoulli's theorem at the topmost point and the point just outside the container in order to find out the velocity. And then I have used the logic that rate of incoming flow of water has to be equal to rate of outgoing flow of water. Only then the level of water in the tank will remain constant. And then I have used the understanding that volume flow rate of water happens to be equal to A into V. So using Bernoulli's equation, we found out V and we substituted that into the volume flow rate of water as the water is outgoing, and the incoming rate of flow of water is already given to be 10 raised to minus 4. Alright, after equating that, we get 5 centimeter to be the answer of this question.